we're going to be talking about environmentally beneficial electrification. For the world to meet its greenhouse gas reduction goals, aggressive electrification of energy end uses such as space heating, water heating, and transportation is essential. Electrification of energy end uses displaces the burning of fossil fuels like natural gas, gasoline, diesel, propane, and fuel oil. This displacement has the potential to significantly reduce greenhouse gas emissions. As my colleague Ken Colburn has prompted me, under these circumstances we're focusing on, quote, emissions efficiency, end quote. I'm going to repeat that, emissions efficiency, rather than simply focusing on energy conservation and arguably turning conventional wisdom upside down. So to explore this in detail, we're fortunate to have an all-star panel today. First, we have Keith Dennis. He's a senior principal in the End Use Solutions and Standards section of the Business and Technology Strategic Division at the National Rural Electric Cooperative Association, NRECA. Keith has a multidisciplinary background in engineering, business, and law, and he works with NRECA's legislative, regulatory policy, and technical teams on issues related to energy end use, including energy efficiency and demand response. We have RAP Principal Ken Colburn, formerly with Symbiotic Strategies, where he provided strategic assistance to numerous states, foundations, companies, and NGOs in their efforts to address climate and energy issues. Earlier in his career, Ken was Executive Director of the Northeast States for Coordinated Air Use Management, NESCOM, and he led the Air Resources Division of the New Hampshire Department of Environmental Services. We also have RAP Senior Advisor, economist Jim Lazar. Many of you are familiar with Jim, who's a principal author of handbooks and articles on rate design, renewable energy integration, integrated resource planning, and incentive regulation. Jim has worked with RAP around the world for nearly 20 years. Before we start the discussion in earnest, let me explain briefly how the webinar is going to work. Our panel will provide about a half-hour presentation. They'll answer questions until about 5 minutes to the hour, and then wrap up with some final thoughts. With that, at the top of the hour, we will end our 60-minute session, but if there's interest, Keith, Jim, and Ken will continue to answer your questions for an additional 30 minutes. Since there are so many of you, we prefer to hold the questions until the panel completes its presentation. The exception, of course, will be the need to address clarifying questions. If there are some, please type them in, and we'll do our best to see that the panel addresses them. This presentation is going to be recorded so we can put it on our website, and you and others can access it at a later time. Finally, we ask that you take a moment after the webinar to fill out a survey. Just a couple of questions, but really important ones. Getting your thoughts will help us be more responsive to you. With that, take it away, Keith.
I think Ken's going to start, Dave.
Okay, Ken.
Great, thanks very much. It's always good, we thought, to start with the end in mind. So with that, I want to offer you our key takeaways. Our end in mind is that more electrification will ultimately lead to less in terms of less risk, less emissions, and ultimately less cost, hence the title of the webinar. Specifically, we think that environmentally beneficial electrification, which we abbreviate to EBE throughout this webinar, is vital to reducing greenhouse gas emissions not only in the U.S. but on a global basis. It's likely to lead to scenarios where more electricity is being used, especially in the foreseeable future, even though fewer greenhouse gas emissions are produced. It will also depend on the use of effective metrics that not only look at energy efficiency, as David indicated, but also at the emissions side too. What we have taken to calling emissions efficiency as opposed to energy efficiency. And of course, as you all know, we need to get going as quickly as possible. Next slide, please. This webinar is drawn from a paper that the three of us authored, which was published in the Electricity Journal in September. And it represents the first formal collaboration between NRECA and RAP. It followed a paper authored by Keith in November 2015, also in the Electricity Journal, introducing the concept of environmentally beneficial electrification with the focus on electricity as the end-use option. In this paper, we focused more on the emissions side, and hence the subtitle of The Dawn of Emissions Efficiency. But let's be clear about our definitions here going forward. Next slide, please. So what is environmentally beneficial electrification? It's not rocket science. It's simply the use of electricity in end uses that would otherwise be powered by fossil fuels, as Dave ran through. And this is in order to reduce greenhouse gas emissions and potentially serve other purposes as well. Next slide, please. That includes, not the least bit surprisingly, the electrification of transportation through EVs, through inclusion of space heating through heat pumps, and water heating also through heat pumps, and also grid integrated water heating. Next slide, please. There is, as David alluded to, growing consensus that the key to meeting greenhouse gas goals, again in the U.S. and globally, is widespread electrification of passenger vehicles, building heating, and I would add water heating, and LB&L said industry heating as well. This is hardly unique to Lawrence Berkeley, United Nations, Columbia, Stanford, E3, the Acadia Center, and many others have reached similar conclusions as those of LB&L. Next slide, please. Even the international agency, as recently as last week, in an infographic heralding the growth of renewable energy, recently implicitly recognized the need for greater electrification in transportation and heating, as we've circled at the bottom of this slide, characterizing these sectors as lagging behind. Next slide, please. And what about emissions efficiency? What do we mean by emissions efficiency? We've long focused on energy efficiency in the quest of reducing the number of kilowatt hours used to accomplish tasks, and thus reducing the number of kilowatt hours that have to be generated, and of course the emissions associated with that generation. While energy efficiency certainly remains a top priority, we don't want to use any more kilowatt hours than needed to accomplish a given task. As renewables penetration increases and other fuel switching occurs, the grid is getting cleaner and cleaner, as Keith will follow up on momentarily. So no longer is every additional kilowatt hour a bad kilowatt hour. This is especially true if that kilowatt hour is used to electrify an even higher emitting fossil fuel end use in transportation and heating. And doubly so if that kilowatt hour has actually been repurposed for this application, having been saved through energy efficiency. That is the result of an energy efficiency dividend, if you will, as Jim will discuss. We're concerned that the metrics used today to develop national policy goals, however, do not recognize these dynamics, and these metrics must shift to reflect the changing technology realities in front of us. So we've introduced the concept of emissions efficiency, reflecting what is the emissions impact of a proposed measure or program or alternative to be an important metric going forward. And in the spirit of Amory Lovin's contraction of negative kilowatts into megawatts, we offer a similar contraction of emissions efficiency into Emiciency to provide a similar shorthand term. Next slide, please. Well, why is environmentally beneficial electrification possible now? It really offers a new potential because we have, in a number of venues and flavors, international, federal, and state policy goals to reduce greenhouse gas emissions. I think you're all familiar with them, the Paris Accord, various federal commitments, including most recently the Clean Power Plan, assuming it survives litigation, and a vast majority of the states with their own RPSs or energy efficiency, resource standards, and so forth. Second, we have a grid that, as I mentioned, is getting cleaner and cleaner, and rapidly so, through not only greater renewables penetration, but fuel switching and heat rate improvements. Third, we've seen dramatic increases in the efficiency of end-use equipment that have led to declining load growth. These are in new TVs, computers, heat pumps and space heating, LED lighting, and so forth. And the generation saved can be increasingly repurposed to fossil fuel end uses, due to technology advances in the transportation and other sectors. We're about to see a 200-mile plus range from EVs. And finally, we all recognize the need for greater flexibility as we manage the grid in order to effectively integrate renewable sources. And a lot of that flexibility can be provided by the demand side, which is represented in electrification, grid interactive water heaters, EV charging paradigms, and so forth. But as we just noted, current metrics and policies, and perhaps even conventional wisdom, will need to change in order to maximize environmentally beneficial electrification. Next slide, please. Fortunately, we have a history of rapid transformation. This slide shows Easter in New York City on 5th Avenue in 1900, and as you can quickly garner, there's no automobiles in that picture. However, if you go to the next slide, this is New York City just 13 years later, Park Avenue this time, and one doesn't see any horses in this one. This pace of change, just 13 years, is not just startling in terms of technology uptake. It also has obviously substantial ramifications for stranded cost risk regarding major new power sector and natural gas infrastructure investments as we look forward to our own 13 years, given that those assets have much longer lifetimes. Next slide, please. It's not just a matter, of course, of horses and buggies. Here's a fuel mix slide. The left-hand pie chart is what EPA estimated in the Clean Power Plan would be the 2030 U.S. fuel mix. The right-hand pie chart shows the U.S. fuel mix for last August from EIA. You can see that really the only difference between those two is that renewables needs to have about a 5% greater shift over the next 14 years to 2030. But we've already seen greater than 20% shifts in these pie slice sizes in the last several years. I'd be surprised, in fact, if EPA's 2030 projected fuel mix isn't achieved even before the mandatory CPP compliance period begins in 2022, assuming, of course, that the rule survives its current legal challenges. Next slide, please, and I think we'll pause for any questions and then turn it over to Keith. Thank you.
Thanks, Ken. There are no clarifying questions, so we can continue on.
Okay, next slide. So thanks, Ken. I'm going to stay on this chart for a second here. This is a chart for from our paper that illustrates the electric sector emissions from 2005 to 2030. The data is from the U.S. Energy Information Administration, or EIA. The solid line here on the left represents actual historical data from the monthly energy review, and the dotted line represents projected data from the annual energy outlook. And the chart shows that we're in the midst of a transition to a less carbon-intensive electric grid. And we're about halfway through the chart here. This change has stark implications on the products that use electricity. It means that anything that's plugged into the grid today will improve in its environmental performance over time. If it's a light bulb, if it's a water heater, if it's an electric car, or if it's anything that's plugged into the grid at some point in time, the chart illustrates that even if it's operated the exact same way, the emissions associated with it will decrease over time. So an electric appliance today performs better than it did last year, and next year it will perform even better. You can also note that the energy efficiency of a specific product will not change over time. That light bulb you plug in today will produce the same amount of light per kilowatt hour over its lifetime. The electric car will travel the same amount of miles per kilowatt hour. The water heater will produce the same amount of hot water per kilowatt hour. So while the energy efficiency will not change over time, the emissions efficiency most certainly will. The amount of emissions per light, the amount of emissions per gallon of hot water, the amount of emissions per mile driven will decrease over time. Now, with direct combustion of fossil fuel like gasoline or diesel or gas or propane or oil, the efficiency of those products you put in today will not only not change over time, but neither will the emissions efficiency because the fuel is the same and the carbon intensity of the fuel is the same. Electricity has a changing fuel mix. And the product choices that we make today, like the heating systems we put into our houses, for example, they last a long time. They can last decades. So we need to look forward and understand these trends so that we can make the right decisions today. This trend that you see here is unprecedented in our history. For decades, the emissions profile has been relatively flat. And during this time, we learned to depend on rules of thumb and metrics that depended on a relatively stable situation. And as this change is occurring, we need to reevaluate our metrics because metrics matter. Prior to this decline in emissions, the way to evaluate electric appliances was relatively simple, again, because the emissions were relatively static. The basic path to reduce emissions from the electric sector was simply to use less electricity. Now it is as or more important when we use electricity rather than how much electricity we use. As the emissions profile of the grid continues to decrease, it will become more and more important to switch away from direct combustion of fossil fuels towards electricity to reap the benefits of these changes. Go to the next slide, please. So again, the metrics really matter. The metrics are set up by the government and regulators and are used to help the public to make decisions. And when they get misaligned, those very metrics that are designed to promote good policy and inform the public's decision can give the wrong outcome. It's important that we get them right because people depend on them. And so we need to make sure they align with our policy objectives and use the most recent data available to keep them up to date, especially when things are changing. It becomes more important when things are changing to keep these things updated. We assert in the paper that emissions efficiency may be as or more important than energy efficiency moving forward. And as Ken noted, we even came up with this shorthand term, Emiciency. And I know it's sort of corny, we will admit that. But my hope is by using this term, we can increase the buzz and get people to remember that technology and policies are changing and metrics need to change too. And what better than that than a new word to know we're in a new time. The paper that we co-authored has 3 examples, and we're going to go to those examples now of the importance of aligning metrics and accounting standards with policy goals. And the first example is going to be presented by Jim Lazar of RAP.
Thanks, Kate and Ken. This is Jim Lazar. I'm coming to you from Olympia, Washington. I contributed to this paper by creating an illustrative example of a hypothetical utility with 100,000 customers. It's a static analysis of a utility that's got a 100% fossil fuel mix, 50% gas, 50% coal. And what I did is I went through this service territory and identified approximately how many customers in that territory would have oil heat, propane heat, electric resistance heat, electric heat pump heat, natural gas heat. The same thing for water heat, and then in vehicles, the electricity, gasoline, and diesel mix. And based on a set of assumptions, I calculated the total emissions for space heat, water heat, and vehicles in tons of emissions per year. And the numbers are set out there, and I don't intend to go through them in any detail, but it was a kind of a disciplined look. Next slide, please. So the first step in my analysis was to implement some efficiency measures. The electric resistance heat for most of the electric heat customers was converted to heat pump heat with a coefficient of performance of around 3, which is very achievable in today's market. And converted most of the electric water heaters, the electric resistance water heaters, to heat pump water heaters, again with a coefficient of performance of 3. That's achievable in today's marketplace. Now, this won't work for every house, and it won't work in every climate zone. In Bismarck, North Dakota, the heat pump water heater in the carport isn't going to perform very well, but in Atlanta, it's going to, or Georgia, it's going to perform extremely well. This efficiency step produced a lot of electricity savings. So if I go to the next slide, we actually calculated a reduction of electric resistance space heat from 30,000 customers to 10,000, and electric resistance water heaters from 49,000 to 10,000. And we saved a whole bunch of kilowatt hours, and we reduced a whole bunch of emissions. We could stop there, and we would have fewer kilowatt hours coming from our 50% coal, 50% gas mix, and less emissions to serve exactly the same electric end uses. But that's only step one. If we go to the next slide, in step two, we took those kilowatt hours that we saved, whoops, back up one, there we go, and we converted some oil and gas water heaters to heat pump water heaters, some oil and gas and propane furnaces to heat pumps, and some gasoline and diesel vehicles to electric vehicles. We used up the efficiency dividend. We took all of the kilowatt hours we had saved and used them to displace fossil fuels in the same utility service territory. So if we go to the next slide, after step two, we've now got all 100,000 customers have space heat, all 100,000 customers have water heat, but many more of them have electric space heat and water heat. And we've converted a number, not a large number, but about 15% of the vehicles to electric vehicles. And we wind up then using exactly the same number of kilowatt hours, producing exactly the same emissions from the electric system, but significantly lower emissions from the end uses, because we have used the efficiency dividend to displace direct use of fossil fuels for space heat, water heat, and vehicles. Over a 20% reduction in total emissions for these end uses. I'll stop there and hand it back to Keith.
Okay. Thanks, Jim. This second example from the paper highlights some challenges with the current greenhouse gas accounting practices that could be improved to also illustrate the benefits of electrification and gets at some of the points that Jim was mentioning. Recently, the EIA released data that shows that the electric sector emissions in 2015 are at the same level they were in 1993, and there were some articles and headlines there. And the headline would make it seem like there's been no change over the last 2+ decades. But if you look at the details, over time, the GDP has grown on average of about 2.5% per year. And digging through the EIA data, we found that in 2015, there are 890 billion kilowatt hours more produced and consumed than in 1993, while the emissions stayed the same. So if you assume that a vehicle uses 3,500 kilowatt hours per year per car, that's enough to power all 253 million vehicles run by gasoline and diesel in the U.S. today without increasing emissions. And that information is not readily gleaned from this data or the headlines that it produced. So now if we were able to just repeat that performance, and I believe with the current trends and technologies, we'll probably easily beat that, but if we were able to repeat that and produce the next 890 billion kilowatt hours with no increases in electric sector emissions, we could power all the vehicles, or we could avoid the combustion of a lot of fossil fuels in space and water heating. Yet we wouldn't meet any requirements of regulations or policies that are simply based on reducing kilowatt hours used, or policies aimed at reducing electric sector emissions. The charts like this one and the headlines might look the same. No change in electric sector emissions despite the progress that has been made due to the environmentally beneficial electrification. And again, it just shows that it's important to manage the goals and incentives properly to make sure that environmentally beneficial electrification is not given a disincentive by accounting practices that don't account for its benefits. If you go to the next slide, this is a third example, and this one involves looking at the emissions we assign to new electric loads. Again, according to the EIA, electric generating facilities expect to add more than 26 gigawatts of utility-scale generation capacity to the grid in 2016. Most of these additions come from 3 resources: solar, natural gas, and wind, which together make up 93% of the total additions. The research shows that using reasonable capacity factor assumptions and emissions rates, this new generation could produce 92.5 megawatt hours per year of emissions at a rate of about 0.19 short tons of CO2 per megawatt hour. This emissions factor is very low, and it could be seen as the incremental emissions factors for electricity that serves new load placed onto the grid, as opposed to the often outdated marginal emissions factors used in policies today. Today we assume that new loads like a new house that's built or an electric car that are added will be powered by a marginal plant, or we just use an average emissions factor. But new loads will be met with new sources, and reflecting the most updated incremental emissions factors for new load would help promote environmentally beneficial electrification, and it would get further us towards the future we envision. So I suggest that you remember, when you can, use that term too, incremental emissions factor. If you switch to the next slide, those are our examples, and we had a great story that was published in a Vox article in September, and it talks about electrify everything, and that's a concept that's been put out there by other academics, and excuse me, ma'am. Sorry, I had a little technical difficulty there. And there's a quote here that says, with electricity, there's a path to zero carbon electricity, but as we've been noting, there's not the same path for combustion of fossil fuels. So if you could switch to the next slide here. So as this regulatory uncertainty surrounds the future of the electric industry, we identified 4 steps that could be taken right away to promote environmentally beneficial electrification without the risk of any regrets of any negative consequences. And the first one we identified was that DOE and EPA could consider updating the source energy factor that are used in policies. And I wrote extensively about this in a previous electricity journal that Ken mentioned, also on environmentally beneficial electrification. And it's a little too detailed to get into, but the basic point is that the source energy metric is the energy efficiency factor of electricity itself. And it's used widely in energy efficiency programs and policies and analysis, even though folks might not be familiar with the exact details of how it's calculated. It's a bit outdated. It's a couple decades old, and it wasn't designed at a time when we were thinking about greenhouse gas policy objectives. One example is that about 19-20% of our grid's fuel mix right now is nuclear energy. When you use a source energy metric, that nuclear energy is treated as about 1/3 as efficient as direct combustion of fossil fuel, because there's a lot of heat lost when you're going through a nuclear process. So if you look at that hot process, it looks like it's relatively inefficient, but it doesn't come out with any greenhouse gases, and it doesn't take any fossil fuel out of the ground. So it's unclear how metrics like this really align with greenhouse gas policy objectives, and they can be a hindrance to promoting environmentally beneficial electrification. So revisiting that's a no-brainer. It takes political will and time because it involves updating technical details of a topic that's not well understood. It's not even well understood by even the most savvy energy wonks. Happily, since the publication of this paper, DOE's made some progress on this issue, and a couple of weeks ago they published a paper that indicates that they're going to be making some changes in the next EIA monthly energy review. So that's good news. It's only for the renewable portion of the grid, but it's a step in the right direction, and I still feel we need a stakeholder process to more fully revisit this metric, and we have a broad coalition of folks who agree with that. Second is relatively simple here. Just when accounting for emissions associated with the addition of new electric load, recognize that emissions intensity of the grid is changing over time. That's the concept of incremental emissions efficiency. Third, as environmentally beneficial electrification is implemented, account for the emissions impacts that result from the displaced direct combustion of fossil fuel, like the gasoline when a car is taken off the road. Finally, move towards emissions efficiency or Emiciency in addition to energy efficiency as a metric for projects that target GHG emissions reductions. And with that, I believe that's the end of this section here, and we'll go to questions.
Great, terrific job, thank you. Let's start, here's the first question. It's going to actually call for you to turn back and look at some of the things you've just articulated. In accounting for the emissions from EVs, should we look at the average emissions rate or the marginal emissions rate for the grid electricity?
Well, I'll take that. You know, I think it's important to look at what's going on with the grid again. If you take a traditional approach where we could just average things out like we have been able to for decades because it was pretty dependable, you'll come up with a very high number of emissions that are going to replace that vehicle, and they tend to be 2 or 3 years outdated. If you instead look at what's going on with a lot of coal coming offline, really efficient combined cycle plants that are coming on, and all that wind and gas that are coming on, you really have to think, what is the incremental load that's going to serve that vehicle? And I think that that there's, as we've been looking at this with environmental folks and others, it really seems to make a lot of sense to use that approach, because if you use just what marginal plant comes on for whole new houses, whole new commercial buildings, it's really not reflective of what's going on, and it can really give you some misaligned policies when it comes to what the benefits are going to be over the next lifetime of that product, which, you know, for a car is well over 10 years.
Yeah, the lifetime of the product is really important. If you can go back to slide 16, please. The measurement should be over the lifetime of the new vehicle, of the new heating system, of the new home. And as we showed in slide 16, as Keith showed in slide 16, the grid is getting cleaner over time. You know, I've got a 14-year-old Honda sitting in my driveway that I expect to drive for another 5 years at least. You know, so vehicles are, you know, last 10 to 20 years. And we need to look at what are the emissions of that vehicle from petroleum going to be over its 20-year lifetime versus what are its emissions going to be if it's electrified. And initially it may be only a small benefit in emissions, but over 5 years, 10 years, and 20 years from now, that electricity will be getting cleaner and cleaner, and the emissions will be going lower and lower. But as Keith said, if you buy the petrol vehicle, it's going to keep burning petrol for its entire life.
Thank you. Electrification, beneficial electrification, has the potential to reduce or eliminate natural gas for home heating and appliances. How does this potential reality impact current policy questions about natural gas pipeline investments, for example, safety, modernization, serving new customers that are fully recovered by ratepayers?
David, this is Ken. I'll start that, and Keith and Jim may have other thoughts. As I alluded, but only briefly, with the pace at which the technology is evolving, both in terms of the graph that Keith and Jim showed with respect to emissions from the grid itself, but also through end-use technologies in vehicles, in end-use equipment, and heating, particularly heat pumps. That is changing so rapidly that the 13 years shown with the horses and cars may actually come to play with respect to the use of natural gas, and certainly increased use of natural gas going forward too far into the future. So I fear that while there is a bridge that natural gas can serve, that it may be a far shorter bridge than most people anticipate, and indeed far shorter than its amortization period, introducing a significant risk of stranded costs for infrastructure projects.
Yeah, regulators may need to look at whether infrastructure projects are cost effective based upon shorter measure lifetime than the physical asset lifetime that has been used for setting depreciation schedules in the past. We don't want to have the same thing happen with gas investment that happened with telecom investment, where when in the 1990s, when telecommunications technology evolved, the phone companies were left with massive stranded cost investments, and it was a major regulatory challenge because the regulators had not engaged in technology forecasting in setting depreciation rates. Many new investments will probably, in gas infrastructure, will probably not be cost effective if electrification is going forward. 26 years ago, I did a study for a client that showed that gas was clearly more economically and thermodynamically more efficient than using electric heat. At that time, the best heat pumps had a coefficient of performance of about 2. Now, almost every heat pump has a coefficient of performance of 3 or higher. At that time, there were no commercially available heat pump water heaters. Today there are. At that time, wind and solar were not real resources contributing carbon-free electricity to the grid. Today they are. If I redid that analysis, my guess is I would come up with a very, very different conclusion. Regulators need to be looking ahead, doing technology forecasting, and determining whether infrastructure is cost effective based on its likely life cycle utilization, not necessarily historic utilization.
Thank you. Slight technical glitch here. Will you please talk more specifically about the opportunities out there for applying this to the industrial sector?
I can mention a couple of things. The idea of beneficial electrification has been out there from EPRI for a while, and they really look at the industrial side as, and it's been more, it hasn't been as focused on the stuff that we're talking about today, which is really aimed at GHGs, but there's all sorts of opportunities for things like forklifts, ports, heavy equipment that can be electrified, and folks are talking on the non-GHG side about looking at areas that have problems with particulates and non-compliance, where you could use some of this technologies, because at the end use you're not producing any emissions, so you can take those emissions out of the point sources and shift them to a renewable resource or somewhere else that's not non-attainment. So there's a lot of things out there in the trucking industry for when trucks are idling, for their refrigeration systems. There's a lot of stuff at airports that are done with idling. So I think there's a lot that can be done. We're really focused on residential, which is a little bit of a harder nut to crack, because you really do need some policy changes. There's some great paybacks that you can do. Another thing is in agriculture, there's a lot of diesel agricultural pumps out there, and they can be switched to variable frequency drives, and they have the benefits of some load management, and they can really reduce emissions as well. So there's not a lack of opportunity out there to do some of this stuff. Dryers can be converted. So there's some good paybacks on some of that stuff as well.
Yeah, the steel industry is probably a great example of this. 30 years ago, nearly all of the steel production in the United States was primary steel production from coal-fueled blast furnaces. Today, nearly all of the steel production in the United States is electric reduction mini mills. They're mostly doing recycled steel. Now that industry has had a tremendous conversion. The ports of Seattle and the Port of Vancouver, as Keith mentioned, are doing what we call cold ironing. When cruise ships come into port, they are connected to the local electric grid, and that allows the ship operator to turn off all but one of the engines of the ship. Cruise ships typically have 4, 5, or 6 diesel engines on board. And so that's dramatically reducing both their oil consumption and their local emissions at the points that they're docked in downtown Seattle and downtown Vancouver.
Yeah, and I would just note that one of the examples showed that depending on where you draw the boundary around the electric sector, that's not getting captured. So as you hear about industry reducing their emissions, and you're kind of saying, oh, that's great. Remember, that's being shifted to the electric sector in some cases, and the fact that we're able to keep the emissions the same and reduce all of those is a great story, and it's not always captured because we tend to put things in silos. So again, if you're trying to just focus on reducing the emissions from the electric sector and you put a cap on that, you could actually accidentally say, don't add any more emissions here or electricity use, when actually adding that there might be a net benefit and might overall reduce emissions, which is why it's important to make sure we're looking at this emissions efficiency concept instead of just looking at one box and trying to maximize that as we have in the past.
Thanks, Keith. One of our listeners writes, I'm confused. We use 890 billion kilowatt hours more today than in 1993. That is not savings, but an increase, right? So how do you convert that to replacing gas cars? Wouldn't that require consuming more electricity?
Well, this is Keith. I think it comes back to the concept that Jim came up with of the efficiency dividend. So over that amount of time, we have just become more efficient at generating those kilowatt hours. So while we are creating the same amount of emissions in the sector, we're able to create more kilowatt hours. With those kilowatt hours, there's enough of those energy efficiency dividend kilowatt hours that they could power all of the cars. Now, we're not saying that retroactively that could happen, but the point is that while it looks like it stayed similar, there's been a big efficiency dividend. And if you take the next step and say, well, what if we could do that again? What if we could keep the emissions the same and produce another 890 billion kilowatt hours, and without increasing emissions? And that would be enough of an efficiency dividend to power all of the vehicles on the road, and to do that without increasing emissions, because you'd actually be decreasing emissions from the gasoline not used. So it's a little bit of a confusing concept, because you're talking about kind of counterfactuals and kilowatt hours that aren't occurring, some emissions that aren't occurring, but that's generally how that works.
Yeah, Dave, if you can take us back to slide 24, where Keith showed the incremental emiscency factor. The overwhelming majority of the growth in electricity is coming from solar, wind, and natural gas has become far more efficient. The new 7HA turbines are over 60% thermodynamic efficiency, on the order of just 650 pounds of CO2 per megawatt hour. If we're a mix of efficient gas and solar and wind serving the growth, and we're displacing petroleum consumption or natural gas consumption. We're replacing natural gas consumption at 80 or 90 or 95% efficiency in a gas furnace with electricity from a very low carbon resource mix operating through a heat pump with a coefficient of performance of 3. We're able to have more kilowatt hours, but lower total emissions across the entire economy. If in addition those cleaner resources are being brought into service to replace older fossil units that are retired as they age out, then the emissioncy, the emissions profile of the electric system improves even faster.
Thanks, Jim. I think your approach of using the CO2 emissions factor for marginal new generation makes sense, if we know what that is.
Well, again, the data from the EIA, you know, comes out and they say, here's what the additions are this year, and generally they'll be in a capacity form, and you can assume some sort of capacity factor for that and say, you know, a megawatt of solar will operate at a certain percent capacity, and you can figure out the emissions profile of that. In the case of renewables, it's generally zero. You can also figure out the coal retirements, and really, you know, this process of figuring out how to account for emissions going forward, it's going to be you know, it's going to be a change. Again, you know, historically, you could take an average from 3 or 4 years ago when everything was just coal or gas or nuclear or hydro, and apply it and be relatively comfortable with that. But when things are new loads are coming on and new generation sources are coming out, there is definitely data out there on what's coming online, what's going offline, and you can use EIA data to project out over the lifetime what will be serving that. And I think there's stakeholder processes and rulemaking processes that could go through, and we could find some common methodologies. They could be local, they could be national, and start using that, because in reality that's what's going to happen from a physical engineering perspective. We need to account for that reality, and I think there's methods that can go out there and at least be, you know, relatively you know, defined, and they don't have to be precise, but nothing that we ever used has been really precise. It just needs to point the policy in the right direction and point the numbers in the right direction, so that we can, you know, make sure that if we have a goal of reducing greenhouse gases, we look at the greenhouse gases of electricity accurately.
And I would just, this is Ken, I would just add to that it's unlikely that snapshots of marginal emission rates will be significantly more difficult to grasp than they are now. They may even be easier. What they will do is be more dynamic over time, but in the right vector, in the right direction. So the key period, once again, as Keith and Jim indicated earlier, is over what period are you looking for those numbers? If you're trying to predict what marginal rates will be going forward, that is very difficult. But again, at least it's declining, which is good news.
We actually have some control over some of these loads that allows us to actually take advantage of times when there are better marginal rates. If we can go to slide 21, the heat pump water heater needs to run about 3 hours a day to provide a day's worth of hot water. With grid integrated water heating technology, we can control when that water heater is running so that it's running when there's a surplus of wind or solar on the system. And it's curtailed when the least efficient fossil generating units are being dispatched. Similarly, air conditioning. We can build air conditioners, and in fact Ice Bear sells them, that have ice storage, or Ice Energy sells them. The Ice Bear has ice storage built into the air conditioner, so that it can run when electricity is cheap, generally, generally when the lower cost and lower emission resources are running, when the sun is shining or the wind is blowing. Make ice and then use that ice, and the only electricity you need at the time you're cooling the building is enough to run the fan system. The electric car, you know, requires about 4 hours to charge to handle 100 miles of driving, but the car is only being driven for 1 or 2 hours a day. we ought to be able to find sometime during the 24-hour cycle when the wind is blowing and the sun is shining, or the most efficient gas generators are operating at the margin, and charge the vehicles then. Smart charging, smart rate design, and smart appliances are going to be a part of this evolution. The electronic controls for controlling the heat pump water heater are built into the water heater already. The electronic controls to control the ice energy ice storage air conditioner is built into the technology already. The charge controller for the electric car is already built into every new electric car. So taking advantage of these control systems to control when we're consuming the incremental electricity, to minimize cost for the consumer and total cost, including societal cost for the society, are technologies that are available to us and that we can take advantage of, and will over the life of these new appliances, even if we don't have all of the pieces in place when the car or the water heater or the air conditioner goes into service today. Over its lifetime, we will be able to take advantage of that technology.
Thank you, Jim. How would you respond to the fact that Europe and Canada have identified the use of new district heating systems for lower quality energy needs, in other words, space and water heating, as critical for meeting EU and Canadian emissions goals, paired with the strategic thermal storage, renewable thermal heat, geo-exchange, and heat pumps? The EU has explicitly recognized that electrification is not the best answer for many heat demands that can be met with lower quality heat, such as waste heat.
I think there's probably a lot of answers to that, and again, Jim and Keith may have thoughts. I think if one has waste heat, then district heating is certainly an advisable path to utilizing it, as opposed to it continuing off or being vented as waste. However, and I should say that there's a lot of waste heat from industrial sources and so forth that's probably relatively unavoidable. However, as the newer sources that Keith mentioned coming on, largely wind and solar, do increase their penetration, as they are rapidly doing in the U.S. and can elsewhere. They certainly don't create waste heat capacity. And so I think in that respect, one would suggest that the EU's conclusions might be accurate for today, but will be less and less accurate going forward.
And I'm not familiar with that specific example in the EU, but I do know they do have policies out there that talk a lot about electrification. And I think one of the points about the technology of thermal storage is completely relevant to electric too. I mean, water heaters, for example, are a form of electric thermal storage, and it gives you the opportunity to store energy that when it's available, when it's cheap, and then not use it when it's expensive. And we do it in different parts of the country, in Texas and up in Minnesota. For example, we have areas where wind is being curtailed and prices are negative. And if you can use that zero emissions electricity at that time to store thermal energy, you can do a lot of the same things. So I believe that in the papers out of Stanford talking about electrifying everything talk quite a bit about thermal storage and its ability. But remember, this is all, you know, we tend to talk about an end state when you talk about, you know, electrifying everything, but there does have to be a path between here or there. And you know, obviously natural gas generating electricity is important, and so are the other fuels that are on the system, and those will generate waste heat. And you could say that waste heat is a zero emissions source. It's certainly not best to waste energy when we don't have to. So I think there's a lot of technical things out there, and when people are thinking about storage, they need to not forget that we can find very cheap storage in thermal storage, electric thermal storage. It's our cheapest storage, and there's a lot of hype around batteries, but we can use these district heatings and water heaters as thermal storage to find a cheap storage solution for these non-CO2 emitting sources.
Yeah, REP has a European group, and neither Ken nor I does a lot of work with them. I've done some work with them in Poland. And Poland has a lot of district heating that's coal-fired, local boilers serving neighborhoods and buildings. And in the short run, for both carbon emission and localized air quality reasons, they're looking at converting those to natural gas. And the question that our Polish team is helping them with is, does it make sense to take that intermediate step, or are there portions of the system where the electrification step should of the end load should take precedence? And there's not a resolution there. I think that there will be some of both that happens. That there will be some areas where if the boilers are in relatively good shape and the distribution system's in relatively good shape, that there'll be gas conversions, and in areas where the entire infrastructure needs to be replaced, that they'll skip that step and move to electrification.
Thank you. So we're getting near the top of the hour, and I think we have time for one more question and a succinct minute or two answer. Many states, including those that already participate in NRECA, are planning compliance with the Clean Power Plan through a mass-based system rather than a rate-based system. What implication does that have for beneficial electrification? Should states considering electrification policies instead plan for rate-based compliance?
That's a tough question. I think in the paper we mentioned that that if you have a mass-based system, some of these things run the risk of not being captured or actually disincentivized. And one of the examples is, if you're up in the Northeast and you have folks who are on fuel oil, and fuel oil prices tend to fluctuate quite a bit, and in the winter they might be kind of running their heat on relatively low because they can't afford the fuel oil, and they've got lye heap and all that stuff. Well, you could switch them over to a heat pump and reduce emissions by getting rid of that fossil fuel and having a really efficient electric system. Now, you're going to save folks money, you're going to reduce emissions, and you're going to make customers more comfortable and save some money, but you're adding load, and that can run afoul of a mass-based system if the boundary's just drawn over the power plants and you're not getting any of the benefits of reducing that fuel oil. So I do think that we need to look at those policies, and the same thing goes for electric vehicles. I mean, one of the potential is that if you have a mass-based system and you don't have any ability to account for beneficial electrification, and you're not meeting your goals, one of the first things you might say is, don't add any new electric load right now. Don't switch over these fossil fuels to electric. And those examples, those little details add up, and they can make a big difference. So I think that folks need to get creative and find a way to make sure that we can add load, and that the policies aren't really focused only on just reducing kilowatt hour sales and electric sector emissions, because that's not the only way. As Jim's example shows, you can have the same power plants producing the same amount of kilowatt hours, and you can reduce your overall emissions. On the rate-based side, there's some things you could do with emissions reduction certificates, but it's a long haul to get the EM&V done for that, and to get those credits, and that's going to be a challenge, and it's one of the reasons why I think these examples really can inform policy.
Thanks, Keith. Ken, we're at the top of the hour. Would you like to summarize?
Sure, I would, and I'd just call attention to Keith's last point that it isn't much different on the on the rate-based side either, because it's the same plants generating the additional load. So rate-based wouldn't be any easier. There's a problem here that we need to deal with. And that illustrates, of course, the conclusions that we shared with you at the beginning of the webinar, that there is a path toward meeting U.S. and global greenhouse gas reduction goals. That path primarily goes through electrification. And so there is a route that we can start to follow. Doing so will end up with more electricity being used. As Keith's bar chart indicated, though, the emissions would be the same or less over time as the grid improves, consistent with Keith's other chart, the line chart. If we interrupt that through policies, then we'll obviously be operating to the detriment of history and the current technology trends that face us. That means, of course, that metrics going forward are critical. Whatever name we call it, emissions efficiency, or whatever, it'll be critical to look at the emissions side, not just the energy side going forward. And, of course, with climate change already upon us, this needs to happen as quickly as possible. So I'd just like to thank everyone for joining us today, and the three of us and our kind operations folks, Dave and others at RAP, will continue for 30 minutes longer if there are other questions. Thank you.
Thank you, Ken, and thanks to NRECA's Keith Dennis and Jim Lazar. This is a great presentation. We're going to send, for those of you registered for this, we'll send you out a link with the recording of this webinar. And as we mentioned earlier on here, this is the formal close of the 60-minute webinar, but there are more questions. And so these guys have planned to stay on, so we're going to close the 60-minute session and catch our breath, and then we're going to start into the 30 minutes of overtime. So back to questions. Can hourly data from ISOs help with this? For example, ERCOT wind integration report showing hourly wind output, Cal ISO renewables daily watch.
I can take a quick stab at that. I mean, when you look at some of these average national programs, a lot of them that I deal with on the end use side tend to take averages, national averages, and you know, there is a lot of discussion about changing things to time variation, and you know, emissions efficiency works with these kind of broad scale national things, but they also work at a device level and at a time level too. So again, the example of a water heater. If you plug it in today, like we said, and you operate it the exact same way, the emissions efficiency will decline over time. Now, also, if you operate it today and you change the way that you use it, you can reduce the emissions efficiency. You can heat the water at night when the wind's blowing, or you can heat it with a solar panel. So,
you said reduce the emissions efficiency. You can improve the emissions efficiency or reduce the emissions.
Right, I misspoke there. Yeah. So you can improve the emissions efficiency by changing the time. So there's more than we can bite off in one webinar or one paper about how important it is to use these metrics. But again, it highlights the fact that, you know, that water heater's energy efficiency, as it's rated by the programs for minimum standards, for example, are gonna stay the same. But you can operate it differently and change the emissions profile. And things like the data that you reference can help to understand that. And right now, I don't think that there's a lot of policies that give credit to those activities. It's a great way for low-income consumers to save money if there's a off-peak rate, and there's other ways. It helps manage the grid, and there's other ways people can get rebates for these water heaters or avoid some of the upfront costs because they get passed on benefits from lower wholesale power costs. In the case of cooperatives, we pass that off to our members. But there's a lot of work to be done to figure out, you know, if from our paradigm of energy efficiency to a paradigm where it's more dynamic, you know, how do we use this information to make sure that we're operating things efficiently?
I mean, in California, for example, where carbon is priced, or in New England where carbon is priced, or in the EU where carbon is priced, the emissions efficiency will flow through the hourly market or the interval market pricing directly. In regions where carbon is not yet priced, it would take sort of regulatory involvement to take the emissions efficiency into account in determining how to control the water heaters and when to control them, how to control the thermal storage devices, how to best price electricity so that electric vehicle owners will charge at the opportune times. Without some form of carbon pricing, it takes regulatory involvement to achieve those societal benefits.
And I just want to add that the other side of that very coin, of course, is the integration of renewables, because in charging at low emission, low cost hours, we're also facilitating typically the integration of renewables. And this, again, mostly on the demand side. So there's quite a web here. It is complex from a macro perspective, but ultimately all of these forces are pulling in the same positive direction.
Okay, next question. I really think that true efficiency and emissioncy should both be examined separately and not combined into one new metric. At the end of the day, solar is only 28% efficient and nuclear is only 35%, if I heard correctly. Yet emissioncy-wise, these both are absolutely great. You do need to look at both separately and then look at the probability that efficiency can be improved as well.
Well, that's something that I've certainly thought a lot about. Again, the idea of the source energy savings is something that was born out of essentially a Jimmy Carter era, where we had fuel embargoes and we were trying to keep fuel in the ground, and we were really looking at the quads of energy saved. And they kind of developed these metrics that looked at source energy, and they really didn't have a great way of evaluating renewable energy back then when this metric was created. And so I guess one of the questions is, it's obvious the problem with wasting fossil fuels in generation. You're taking gas or coal and putting it in a power plant, and you're losing some of that. It's not as obvious about sun rays that are renewable, that aren't being taken out of the ground, that would otherwise just be not turned into energy and losing them. So when you say a solar panel is only 28% efficient, I mean, I guess that really depends on how you look at it. There's also, sun that doesn't hit the earth and all sorts of other things, but the point is that it's renewable and carbon free. So if the goal is to reduce emissions in a specific policy, I'm not sure how relevant the 75% in that specific calculation that somehow wasn't converted into energy is. It's certainly better to make the panels as efficient as possible. And the same thing sort of goes for nuclear. Again, when these efficient metrics were made, the example you could use is again, I tend to use a water heater. If you're using a gas plant and the gas plant's only 30% efficient, an older gas plant, and you're losing 70% of that gas in the transmission and distribution, or you could put it on site and use something that's 60% efficient, the rule of thumb would be, well, burn it on site because you're going to save gas that way. With nuclear, you can't really have a nuclear reaction in your water heater at your house. So, and it's just a hot process. So, how much energy is lost between that fission and getting the electricity to the house that's not generating any CO2? It's sort of the product of a different era where we're looking at. But the broader point that energy efficiency and emissions efficiency need to be separate, and that both are important goals is not lost on us. I mean, the example Jim gave was how they work hand in hand, and you don't want to waste, as Ken had said at the top, you don't want to waste energy in doing the same service that you otherwise could with less energy. But really the question of how much renewable energy is not making it into the solar panel, I just don't know if they're as relevant as they were when we were talking about kind of the older generation fleet.
Yeah, I'm looking outside at a blue sky, and a tremendous amount of solar energy is being spilled, not being used in solar panels to produce anything, and it looks terrific to me. I don't see it spilling solar as having exactly the same same impact as stack emissions from fossil combustion, even if the fossil combustion is more efficient. In the study that I did 26 years ago, I looked at burning gas in combined cycle power plants that at that time were 42% efficient to operate an electric resistance water heater, and compared that to burning gas in a gas water heater. And in that comparison in 1990, using gas on site was by far the more thermodynamically efficient process. It had the lowest cost, it had the lowest emissions, and had the lowest fuel consumption. But today, where we might be powering a heat pump water heater with a coefficient of performance of 3, we might be serving it half with carbon-free electricity from solar or wind or nuclear, and half with efficient gas generation from a new gas unit that's 60% efficient. We're going to be using 1/4 as much gas and producing 1/4 as much emissions to get the same amount of hot water as would have been the case with direct application of gas. It depends on the efficiency of the appliances. It depends on the fuel mix of the utility and the efficiency of the fossil generating units on the system. And as Ken said, all of those are moving in a favorable direction for electrification.
Thanks, Jim. If the renewables are not being curtailed, meaning their entire generation output is being used to serve the existing load, wouldn't the incremental load added by EVs be served by dispatchable fossil fuel generators? In other words, if renewable generation curtailment is not currently an issue or expected to be an issue during the lifetime of the electric car, then the emissions from EVs should be calculated based on the emissions rate from marginal fossil fuel generation, not the average emissions rate of the new renewable generation added.
Well, it would be the marginal emissions of dispatchable resources, not necessarily dispatchable fossil resources. Nuclear units are being cycled today to meet load, and in fact that's one of the reasons that several of them are closing, is that they're not able to be competitive. But yes, if there were no renewable curtailment being experienced or anticipated over the life of the car or the water heater or the heat pump, then you would be looking at this dispatchable resources, most likely fossil. But the renewable opportunities are so strong, that we're seeing renewable curtailment in the Pacific Northwest, we're seeing renewable curtailment in California, we're seeing it in Hawaii, we're seeing it in Iowa. So all of the regions where we're seeing it in Texas. So all of the regions where there's a significant development of as available renewables, we're experiencing some curtailment now. And as the fuel mix shifts over time, I think we'll see more and more curtailment.
And I think there's also a point to be made here about the flexibility of these resources. Again, historically these power plants that are running on coal and gas were built to meet load, and you could always make them run. And so the idea was just to build a power plant that met the load. Now we have these renewable resources that just come on when the wind blows or the sun's shining, as everybody knows. And it's more important now to match the load to that generation. And so when folks there's camps out there that say integrating a lot of renewable resources is going to be super expensive and make things unreliable. And other folks say, well, we'll do it easier and cheaper than we think. Well, one of the ways to make it easier and cheaper is to make sure that we have the flexible resources and tools in order to do that. And these resources that like a vehicle or a water heater can be turned off or turned on to match those loads without anyone noticing. You'll still be able to drive your car the same amount. You'll still be able to get the hot water. So there's a valuable, and you have to also think, you know, what is actually happening at that time when we're short on power, and it might be that cars stop charging and water heaters stop charging, and that's actually what's going on, and not necessarily the marginal power plant. But I think you know, all of these things end up being sort of a rounded into a policy, and I think that when you're thinking about these new loads, you have to be forward thinking about these trends, because, and it takes a mind shift, because it really does throw, like they said off the bat here, throw conventional wisdom on its head. It's a little bit different than it was in the past, and we need to think about how to change, because you can see that things are changing, and to kind of hold on to the old metrics, because that's the way of thinking, you know, is not going to get us to where we need to be.
Do you recommend that cities that want to be progressive on climate change policy eliminate rebates for natural gas appliances?
And this is the compared to what question, David. And it also is a question of which appliances. You know, if somebody needs a gas cooking range, there isn't a heat pump cooking range to my knowledge. However, I think that that is a wise path, or at least to match those incentives to heat pump technologies when those technologies exist, as they do with space heating, water heating, and electric vehicles.
I'll give the same answer I gave before, is one should look at what are the emissions and costs going to be over the life cycle of the appliance. And for those cities that have executed the mayor's pledge, you know, do gas appliances enable achieving an 80% reduction by 2050? If the cities have adopted that as a goal, they need to be thinking about whether gas appliances are helping or hindering achieving that goal.
I'll give a example out of California that a gentleman told me, and I don't work a lot in California, so correct me if I'm inaccurate, but my understanding is they have an 80% greenhouse gas reduction goal, and it's not really pegged to population growth. So if you're talking about the reductions from electricity, they were saying to me, and whether it's 80 or 90%, it's about an order of magnitude less emissions with the electricity by I think it was 2050. So that emissions reduction is going to be significant, but because we've developed these rules of thumb that Jim had, you know, kind of analyzed before there was heat pumps and before there was a lot of renewables, the state has essentially made it very, very difficult to put in electric water heating. So they have, I believe, in the 70% market penetration for gas. And you know, you do have to question if you're going to have an order of magnitude less emissions associated with the generation side, and then you have a product on the other side that's 200-300% efficient, or even, you know, a controllable water heater that will help eliminate the duct curve. You do have to think, you know, are those rules of thumb really serving you well?
Great. Do you have any more recommendations on how we may need to address the disincentives in the Clean Power Plan? Would updating the source energy factors you mentioned help with that, or are bigger changes ultimately needed?
Keith, I'll let you take the source energy factors. I don't think that they would make that much of a difference. Those are really useful in comparing appliances, but perhaps less so in terms of a rate versus mass kind of compliance scheme going forward.
Yes, you know, on the source energy thing, that tends to be in you know, appliance standards and building benchmarking, home rating systems, where you might have gas and electric in a house, and you're given a score and given a rebate for how you're doing. And if the electricity is you know, being penalized for losses in the solar rays that aren't converted to electricity, or the nuclear that's lost in the fission process, and it's being multiplied by 3, you're going to get lower scores, and it's going to incentivize people to use end uses. On the specific Clean Power Plan policies, you know, maybe that's an issue for RAP, but you know, again, it seems to me that you really want to avoid disincentives for adding things to a system that at the same time you're trying to decline the emissions from. So it seems like, you know, when there's a train leaving, you want to get on the train, and the train's going with the emissions down as the last time, you want people to get off. And if you do it incorrectly, people are going to switch away from it at the same time you're trying to improve it. And that seems to me to be counterproductive. And I don't know if Ken or Jim have any more specifics on.
Well, I think that there is a structural problem in the Clean Power Plan's framing at this point, in that the efforts that we've all described here would not help jurisdictions comply either from a rate-based or a mass-based perspective. However, I think that structural problem is not tomorrow, because the increasing penetration and ability to manage renewables through other means, evidenced in those pie charts that I showed, are likely to make compliance with the Clean Power Plan as finalized reasonably easy. So this is a problem, and it will eventually break, and probably in the not too distant future. I'm not sure that anybody's run those numbers about where these lines intersect, declining emissions due to increasing renewables and fuel switching versus greater electrification with what remaining emissions do exist on the grid, even though the grid's improving. But they will intersect, and at that point there is a structural problem with the Clean Power Plan.
And one other thing I just remembered is, you know, we just put in these comments for the Clean Energy Incentive Program that were due a couple of days ago, and that seems like a voluntary program that has a structure that could live beyond this it may have some more flexibility than the actual rule itself. And it's important to think that, you know, low-income folks that are trying to be benefited by programs like that might be on fuel oil, and they might want to get off. And so one place where there might be some flexibility is to look at whether things like changing out fuel oil to heat pumps should be allowed, or even agricultural pumps from diesel to electric. It might be a foot in the door that goes around some of the structural problems that Ken's talking about.
Thank you. I have heard the argument that a state's decoupling policy would need to be revised to encourage electrification of vehicles. However, as I understand the presentation, the electrification of transportation would accomplish this through energy efficiency elsewhere. That would seem to suggest that decoupling policies need not be touched.
I can make a broad point about the example, and Jim's the expert on the example, but when we set up these examples in general, sometimes they isolate things to an ideal situation, and I think one of the broad points here is that we wanted to have the kilowatts before and kilowatt after be equal, and Jim devised that efficiency dividend, which is happening in real life. Now, in real life, things are much more dynamic. There's efficiency going on. There's loads being added, loads being taken off. There's the generation sources don't stay the same, but it really illustrates a point. And the point shouldn't be taken to mean that that's what's happening. That problem, or that point that's illustrated in the example is out there and needs to be fixed. But there may not be the opportunity to, you know, water heaters, for example, only break once every 12 years. There might not be the opportunity to get that efficiency dividend fast enough to do some of the things that we want to do. So it shouldn't be necessarily thought that the efficiency dividends are going to grow at the same pace as the beneficial electrification opportunities. So that's just a broad point on the example.
I'll speak directly to the decoupling part of this. There are two general approaches to decoupling. Revenue per customer decoupling, where the utility is allowed a specific amount of non-power revenue per customer to cover the cost of the distribution system and operating costs. And attrition decoupling, where each year the commission looks at what has changed on the system and sets a new revenue requirement, which is then recovered independent of, trued up for whatever the sales volumes happen to be. An attrition decoupling system, such as used in California and used in Hawaii, would not need to be changed at all to accommodate beneficial electrification, because each year the commission is looking at how much was spent to upgrade the distribution system and what has changed in sales. And if distribution system upgrades were needed to accommodate beneficial electrification, it would be accounted for. If power supply improvements were needed to accommodate beneficial electrification, it would be accounted for. In a revenue per customer mechanism, if distribution system, and we recommend that approach be used for distribution only costs, so for the distribution utilities in the competitive states, or for the distribution component of cost, as for example, Puget Sound Energy's decoupling mechanism only addresses distribution costs. That decoupling mechanism, for a revenue per customer mechanism, may need to be modified, and there's something called a K-factor that can be used in revenue per customer decoupling, and is for Puget Sound Energy, to adjust the allowed revenue per customer over time to reflect changes in the distribution infrastructure that's there to be recovered. REP has a new publication on decoupling that will be available by the time of the NRECA conference in 2 weeks, and it will be available on our website at that time on tailoring decoupling for local conditions. And while we don't specifically address the beneficial electrification issue in that paper, the principles and methods that are addressed in that paper provide guidance for how to address something like electrification that would change the trajectory of electric utility investment per customer.
Thanks, Jim. Okay, so we have maybe a minute or so left. So the lightning round, folks, very brief responses. There was a comment about the time of consumption being as important as the source fuel. Does your analysis contemplate opportunities for off-peak electric thermal storage? Is there an opportunity to increase the load factor for co-ops, for example, with this type of technology shift?
Well, I certainly think that having an increased load factor increases the efficiency of the system, and one of the things about this is making sure that people are not disincentivized to do those things. And I think broadly speaking, you know, the time challenge is something that would factor into a Emiciency way of looking at things. So I think that all of that fits very well with trying to align the policies with what would be optimal for the grid.
Yeah. I will have to add to that. You may actually be decreasing the load factor in order to take advantage of as available power. You know, in a thermal power world, high load factor was considered very desirable to run power plants as uniformly as possible at their highest efficiency output and only have as many as you need. In a variable renewable world, you may have wind that blows 40% of the time and solar that produces 40% of the time, and some of that time overlaps, and you need to store that energy in thermal storage, in water heaters, in air conditioners, or in electric vehicle batteries or other batteries. to use when the wind isn't blowing and the sun isn't shining. So you may actually wind up decreasing system load factor in order to improve emissions efficiency to take advantage of the variable resources when they're available.
The only thing I would add is I think the questioner has it exactly right, except that it's not limited to co-ops. I appreciate the co-op angle, but certainly would also apply equally to IOUs.
Well, once again, thank you to Keith Dennis, Jim Lazar, and Ken Colburn. This has been a terrific presentation. Our thanks to all of you for joining us. Remember, we'll be sending you out a link shortly to this webinar, and if you would please just take a moment and answer the 2 questions that we posed to you when you leave this presentation. Hope you all do well, and hope you enjoy the rest of your week. Thanks, you guys, and I think that's it from Montpelier.
Thank you.
Thank you.